Hello everyone, welcome back. This is actually the last video in this quick introduction to number theory, and what we're going to talk about today is multiplicative order and primitive roots. So last time we were talking about Fermat's little theorem, and what we noticed is that when you have a prime, you're working modulo a prime, the 10th power, so the p minus 1th power of every unit gives you 1 modulo p. So that the fact that there are ones in this column, that is the statement of Fermat's little theorem. But it is not true that every unit to the 10th power, that is the first time you get a 1. You can see that 1 to the 1 is 1. 2, the first time it happens is 10. But for 3, that's not the case. For 3, the first time it happens is for 5. And for 10, it's not 10 to the 1 is not 1, but 10 to the 2 is 1. So the first time you hit a 1, that is called the multiplicative order of an integer modulo p. And that has, well, a special name. So we're going to define it. So here's the definition of this concept. We say that, so let, whoops, not calligraphic, let m be a modulus and an integer a that is relatively prime to m. Then the multiplicative order, sometimes we just say the order of a modulo m is the smallest positive integer k such that a to the k is congruent to 1 modulo m if it exists. Okay, we haven't proved that that is the case, but it turns out that it is the case that there is such a number. So for example, what we just saw is that here the order of 1 is 1, because 1 to the 1 is 1. The order of 2 is 10. The order of 3 is 5. The order of 4 is 5. The order of 5 is 5, but the order of 6 is 10 again. So let me write that. For example, modulo 11. I'm going to write a little table of a modulo 7 and its order modulo 7. Okay, that's how I write the function order. I'm going to write ord of 7 of a, or order of a modulo 7. And here are the possibilities for a. Oops, I wanted to do modulo 11 first. We'll do modulo 7 in a moment. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the orders, as I said, the order of 1 is 1. The order of 2 is 10. The order of 3 is 5, 5, 5, 10, 10, 10, 5, and 2. How about the orders modulo 7? One can check that the orders are as follows. Modulo 7, the possibilities are 1, 2, 3, 4, 5, and 6. And the order of a modulo 7 are as follows. 1 has order 1, 2 has order 3, 3 has order 6, 4 has order 3, 6, and 2. For example, we can check this here. Let's see what happens with the powers of 2 modulo 7. The powers of 2 are 2. 2 squared is 4, but 2 to the 3 is 8, and 8 is 1 modulo 7. So 3 is the first time that a power of 2 hits 1. For 3, I get 3. 3 squared is 9, and 9 modulo 7 is 2. 3 to the 3 will be 3 times 2, 6. 6 times 3 is 18, which is 4. 4 times 3 is 12, which is 5. 5 times 3 is 15, and 15 is 1. So this corresponds to 3 to the 6. So 6 is the order of 3. Okay, so the fact that the very first time we get a 1 in the powers of 3 is 3 to the 6 means that the order of 3 is 6. What about for not modulus that are not prime? Let's see an example of that. So here are the powers of numbers modulo 15. I'm only putting here the units modulo 15, and let's see what the orders are. So the order of 1 is 1. Let's make a table as we go along. So what is a modulo 15? I'm only going to do units. And what is the order of a modulo 15? The units are 1, 2, 4, 7, 8, 11, 13, and 14. And the order of 1 is 1. The order of 2, you can see that it's 4. The order of 4 is 2. The order of 7 is 4. The order of 8 is 4. The order of 11 is 2. The order of 13 is 4. And the order of 14 is 2. Here it is, the first ones. Okay. So what you can see here, though, is that even though there are 8 units, all the cycles are kind of short. There is no cycle that cycles through all the units. That was not the case for 11. You saw that there were some very long cycles. This cycle is particularly nice because it cycles through all the units as it goes through the powers in some random order, but it cycles through all the units. That does not happen modulo 15. And so let me give you a couple of results that are useful about the order. Also, like what kind of orders can we get? Can we just get any number as an order, or is there a reason why the orders are 1, 2, and 4 here? And is there a reason why the orders are 1, 2, 5, or 10 here, or there are 1, 2, 3, and 6 here? You can see that this 1, 2, 3, and 6 are the divisors of 6, while 1, 2, 5, and 10 are the divisors of 10. And here, there is 8 units, and the numbers that I get are 1, 2, and 4. I get divisors of 4, but I do not get an 8. But instead, 1, 2, and 4 are divisors of 4, which are, so it's not, there's no cycle of order 3, for example. So what is the definition? What I wanted to say here is that, so let P be a prime for now. And we have an integer that is relatively prime to P, so it is a unit. And suppose n is bigger or equal to 1, such that a to the n is 1 modulo P. So suppose that I do have some power of a that gives me 1. Then two things happen. First of all, the order of my number, whatever is the first time it happens, it's actually a divisor of n. So if the order was 5, then the possibilities for the other numbers that a to a number will give me 1 will be multiples of 5. And 2, the order is in fact a divisor of p minus 1. Why? Because I know that by Fermat's little theorem, so this is actually implied by Fermat's little theorem, plus part 1, because Fermat's theorem tells me that a to the p minus 1 is congruent to 1. So what this says is that every order, when the modulus is prime, has to be a divisor of p minus 1. So for example, what we've seen before is that the possible orders modulo 7 were 1, 2, 3, or 6, and they are all divisors of 6, which is 7 minus 1. The possible orders modulo 11, we just saw they are 1, 2, 5, or 10, and these are divisors of 10, of 10, yeah, which is 11 minus 1. Okay, so that's why those orders happen. For the third part is that if m is some other modulus and a and m are relatively prime, then it turns out that the order of a modulo m divides phi of m. And this I haven't talked about, but it's a consequence of Euler's theorem. Okay. And for example, remember that the when m was 15, the orders that we saw were 1, 2, and 4. And phi of 15, if you remember how to compute values of the Euler-Phi function, the Euler-Phi function is multiplicative on relatively prime factors. So this is phi of 3 times phi of 5. And phi of a prime was p minus 1. So this is 2 times 4, 8. So the fact that these are divisors of 8 is explained by Euler's theorem. The fact that there is no 8 happening as an order, that is not explained by Euler's theorem, but is explained by what we call the primitive root theorem. So it turns out that these elements, the elements such as 2 here, elements that their order is 10, and 10 is as many units as there are very special, and they're called primitive roots. They're primitive roots, and they are special because the powers of them generate all the elements, all the units. And we use that in cryptography because this order that the units come in is very random in a sense, and that randomness can be exploited to create codes, to create cryptographic methods that are actually hard to crack. So let me define what a primitive root is first. Definition. Let's do it. So let m be an integer. We say that G mod m is a primitive root if the order of G modulo m is the maximum that is possible, which is phi of m in this case. So if m is p a prime, then G mod p is a primitive root if the multiplicative order of G modulo p is p minus 1, which is the value of phi at a prime p. Okay, so for example, for p equals 11, the numbers 2, 6, 7, or 8 are primitive roots. and that comes from the table that we had here at the beginning, because 2, the order is 10. For what did it say? 6, 7, and 8, the order is also 10. And for no other number, the order is 10. So those are precisely my primitive roots. For p equals 7, there are also primitive roots. And the primitive roots are 3 or 5. Okay, and I think we also went through the powers of 3 and showed that the powers of 3 cycle through all the units modulo 7, and that the order of 3 is precisely 6, equal to 7 minus 1. However, when m is 15, there are no primitive roots. A primitive root would have order, there's no element modulo 15 of order phi of 15, which is 8. So if we go back to our table, we see that even though every element to the 8th power is 1, which is what Euler's theorem predicts, however, there is no element whose order is 8. They are all the orders happen before 8, 1, 2, or 4, and never 8. So there's no primitive root modulo 8. And one of the big theorems one proves in number theory is the existence of primitive roots. So this is called the primitive root theorem, and it tells you the following. So let p be a prime number then there exists a class G modulo P such that the order modulo E of G is P minus 1, i.e. G modulo P is a primitive root. Or in other words, which is the condition that we really like, is that the units modulo P are actually given by, which we know are all of these numbers, mod P, they're actually given by the powers of G to G to the P minus 1 modulo P are precisely the units. And another theorem is that there is there is a primitive root, and in fact there are phi of p primitive roots modulo p. So there are phi of p minus 1 primitive roots. However, finding primitive roots is very hard, and it's a difficult problem. We have conjectures about primitive roots, but we don't have a good algorithm to find primitive root. Okay, very good. I'm going to finish with describing what is what's called the discrete logarithm problem. So what is, you might have heard about the discrete logarithm problem, and the problem is the following. Let P be a large prime. And we're going to take a field of P elements, which for us is just going to be the Z mod PZ. Okay. And we're actually just going to take the units. in the field of the elements. So those are the units. And we know that there is a primitive root. Let G be a primitive root modulo P. Then the discrete logarithm problem, the discrete log problem is the following. So given P and G as above, and 1h in FP cross, so on some unit, find x bigger or equal to 0 such that G to the x is congruent to H modulo P. So, and then we call x to be the discrete log of H in base G. And we write it log H of G, or sometimes we actually, because it's not a logarithm in the sense of the real numbers, we use instead indices. So it's the index of H in base G. Remember that when there are primitive roots, all the units are powers of G. So if I take any unit, H, there has to be a power of G that gives me that H. But finding that problem X is hard. So for large primes, this is a very hard problem. And again, there are cryptographic methods that are based on the fact that this is a hard problem to solve. So giving a very, very large prime P with lots and lots and lots of digits, and I give you, for example, a number 3, and I give you a primitive root. What is the power of that primitive root that gives me 3? So there has to be one power that does that job, but what power that is, it's very hard, because there would be, if P has like 300 digits, then there is a lot of exponents to check, and there is no known way of finding X in an efficient manner. Let's try to solve the discrete logarithm problem in one case. So P is 13, which is not a very, very large prime. G is 2, and H is 5. Okay. So I want to know so the question is, what is the logarithm in base 2 of 5? So what we're looking is for a power of 2 that will give me 5 modulo 13. So in this case, I can just start trying powers of 2 and see if I get 5. That's all I can do with what I know. So I can start with powers of 2. 2 squared is 4. 2 to the cube is 8. 2 to the 4 is 16, and 16 is 3 modulo 13. 2 to the 5 is 3 times 2, 6. 2 to the 6 will be 6 times 2, 12. 2 to the 7 will be 12 times 2, 24. That is 11. 2 to the 8 is 2 times 11, 22. And 22 is 9. And 2 to the 9 is 9 times 2, 18. And 18 is 5. So we've broken the discrete logarithm problem, and what I know now is that the logarithm in base 2 of 5 is is 9. Okay, but now try to do the following. Try to figure out if P is 4001 and G is 3 and H is 5. Try to figure out what is the logarithm in base 3 of 5 for 4001. Well, I'll give you the solution, and you can try to figure out a way of doing this without doing a lot of computations, and there is no known way of not doing a ton of computations. It turns out that the logarithm of 5 in base 3 for this prime, 4001, is 1180. So you would have to do more than 1100 computations before you actually find what is the logarithm that works. So that's it for now. If you want to know a lot more about number theory, what I suggest is that you go to my website, my academic website, and you can find over there, let me write that, this, UConn. You can find a book that is free. There is a free PDF that you can download there, Number Theory and Geometry, that covers all these topics in a lot more detail. And from there, you can get a much more solid understanding of the proofs of all these topics and some more examples and so on. I will perhaps do a follow-up to these videos with some of the cryptographic methods that I will be discussing in my class in the fall. So I'll stop here. Thank you for listening.